Now, this does not mean that we have to read it out of your book in this form. This just means if we can manipulate it, move things left and right, and so on, and beat it into the following way. So if we can write it in this form, we say it's linear. So let me write it down. We'll talk about it. A sub n of t, d nth derivative of x with respect to t, plus dot, 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 dot. We'll talk about that in a minute. A sub 1 of t times dx dt, plus a sub 0, or a naught, however you want to say it, of t times x is equal to e of t. Okay, if you can write a differential equation in this form, which has a lot of dots, the reason we have the dots in here is because you might have three derivatives, a third order derivative, or a fourth order derivative, or a fifth derivative, or a second derivative. Depends on how complicated your equation is. So we kind of have the dots in there to tell you we can make it fit the problem. So what we basically have is, you have a lot of things written down in front of you. So let's just break it apart real quickly. Here we have the derivatives. This could be fourth derivative. And then the next guy below it would be third derivative, and then second derivative. And here we've written the first derivative out. After the first derivative comes no derivative. It's just x of t. So you just go down in derivatives. So, fifth, fourth, third, second, first, and then no derivative. This is just the regular variable. Okay? That's what the derivatives are. Don't let the n scare you. This is just a placeholder. I don't know how complicated my equation is going to be. We're going to say it's nth order. Could be seventh order. Could be 10th order. Whatever. All right. Now we have a constant. I call it a constant, but really it's a function of our independent variable time sitting out in front of every single term. So the sub n here, don't get so confused by that. That follows the same numbering that we have here. If it's fifth order or fifth derivative here, then we say this is a sub 5. A sub 4, a sub 3, a sub 2. Here's a sub 1 because this is the first derivative. So these are just subscripts to keep track of the fact that they're different constants. And I keep saying constants because later on in the course these are going to be reduced to constants to make some solutions easier to deal with. But right now this is the general thing. In general, they can be a function of time. If your derivatives in your book are written instead of dx dt, if they're written dy dx, same exact process follows, but if it's dy dx that you're looking at, then this will be a of x. It follows the independent variable here. So the function that it's a function of, or the variable that it's a function of, follows what's on the bottom here, the independent variable. So the way to really look at this is basically the following. We have n derivatives, however high you want to go in the complexity of your differential equation. You have nth derivatives. In front of every term here, you have a function of, in this case, time, a function of time, a function of our independent variable. This guy, this a sub n of t, could be any function of time. Could be square root of t. This could be sine of t. This could be logarithm of t. This could be 1 over t. It could be any function of time. So you could literally have some derivative with any function of time in front of it. Here you have a first derivative with a different function of time in front of it. That's why the subscripts are numbered differently. Could be a different function of time in front of this term. And this guy could be a different function of time in front of this term here. So that covers the left-hand side, and it covers an extraordinary amount of equations. On the right-hand side, we have e of t, and we've talked about that both in the last section and also in the previous volume of differential equations. We have these equations set up. The left-hand side is basically going to describe the system. What are you talking about? Are you talking about a mass on a pulley or a mass on a spring? You're talking about fluid flow. This is going to just sort of describe the system. What's on the right-hand side, this function of time that's off by itself, is what we call the input function or the forcing function. It is basically dealing with, are we injecting anything into the system to force it to do something? And if we are, then this function of time is going to be, some function of time, whatever we're injecting into the system, some force or some flow or something like that. But if we set it equal to 0, then we basically don't have an input forcing function, and we're just looking at the system response as a system, but we're not actively pushing on the spring or whatever. We've talked about that pretty extensively. So if we can write an nth order differential equation in this form, we say it's linear. There's a lot of history as to why this is called linear, but this is what it means. If it's anything other than this, it's called nonlinear. And nonlinear differential equations are much, much harder to solve than even these, which pretty soon here in the course you'll start realizing that even these can be difficult to solve at times. So if you have a nonlinear equation, many times they can't be solved at all without a computer. And that's just the case with differential equations. A lot of times you get into cases where you can't solve them at all unless you pull out a computer and have it numerically kind of solved by converging on a solution numerically instead of symbolically. Okay, so linear differential equation. That was the point of writing this on the board. If it has a forcing function out here, we say it's non-homogeneous. If we set this equal to 0 over here, we call it homogeneous, and we've been talking about that in previous courses. Okay, so we'll write that down. It is homogeneous if E of t equals 0. Homogeneous if E of t is equal to 0 because there's no forcing function. We call it non-homogeneous if E of t is anything other than 0 because there's some kind of external forcing function going on there. All right, so let's write the following thing down. And this is sort of like one of the main things I want to get across in this section. Solving this linear, I'll go ahead and underline linear again, linear ordinary differential equation, which is really what we're going to concern ourselves with for almost the entire DVD, always yields solution of the form, and this is very, very important because it's going to come back again and again and again and again. It always leads to a solution of the form x of t, because don't forget, that's what we're always trying to find. What function of x satisfies that differential equation is equal to some set of constants times h of t, and I'll explain all this in a second, plus p of t. All right, now let me write all this stuff down. There's a few things I really want to get on the board before we start really picking it apart because there's a lot of stuff here. All right, so what is p of t? This is what we call a particular solution to the, I'm going to put n in parentheses. N means non-homogeneous, so I'll go ahead and write it out. Non-homogeneous. Anytime I have parentheses n, that means I'm talking about the non-homogeneous version. It means the version that has E of t over here. Version. Let me get that on the board, okay? And then let me write something about this, and then we'll talk about all this stuff. So don't stress out if you don't quite get it yet. This term is a solution to a homogeneous version. I'll put H, version, which leads to, that's what the arrow means, an infinite set of solutions. All right, so this is a lot of information, and really, to be truthful, I have two goals in this particular section that you're watching right now. The first goal is to explain what linear differential equations are and to give you some practice in the following problems here, at least solving some really basic ones that don't require a lot of technique, but you need to get some practice with solving the easy ones before you go into the harder ones. The second thing is, the second major thing about this section is I really want you to understand what I'm talking about here. It is absolutely central because as we go further in the solution techniques, you'll see this pop up quite a bit. You'll see it in your book, and you'll also see me refer to it. So it's really important that you understand. So let's pay attention to what we're talking about here. What I'm telling you without any proof at all is that if you have a linear differential equation, which this describes a ton of different equations, lots of different derivatives, different functions in front of the derivatives, with any kind of forcing function I want, it will always lead to a solution that looks like this. This is the general class of the solution. It will always work. All right. One part of the solution over here we call P of t. It's what we call a particular solution to the non-homogeneous. That's what we have in a particular solution to the equation when I have this forcing function over there. Okay. And the other part of the solution is the way I write it in the shorthand, and a lot of books write it in the shorthand, is constant times h of t. H of t means homogeneous solution. So if I take this equation and I put a 0 here, right here, so I replace my forcing function and I put a 0 there, and I solve that differential equation that results. We've done that in volume 1 of the differential equations tutor a lot of times, even for the first order equations. When you put a 0 in there, you're solving what we call the non-homogeneous version. It's like if I have a spring system and it's being driven by some mechanical arm, that E of t is the pushing function, the forcing function. That is the real, the real system there with the forcing function involved. But a lot of times it's kind of like decomposing vectors. When you have a vector, it's at an angle, it's better to split it up into 2 directions. That was a really new concept, years ago when you first learned about vectors, right? Well, in differential equations, it's kind of the same thing. It's really, really useful to take your differential equation with your forcing function and look at solving the system when the forcing function's gone. So we can take that spring system, put a 0 here, and then we say we solve the homogeneous version. Now, there's no pushing function, but what we're solving in that case is like the system response to, the spring constant, the mass, gravity, friction, all of the things that are involved if you just kind of pulled it and just let it go, but you don't continue pushing on it, you just see how it responds. Different amount of viscosity in your lubricant, different amount of spring constant, different amount of mass is going to lead to a different homogeneous solution with no forcing function. So it's kind of like decomposing vectors. You look at this long equation and you put a 0 here just to see what the system is doing. This leads to this part of the solution. CH of t is a shorthand way of basically saying whatever I get as the solution here, I'm going to have a bunch of constants and I'm going to have other functions of time mixed in with these constants. This whole collection is what we call the solution to the homogeneous guy. I say that it leads to an infinite set of solutions because the solution to the homogeneous equation is always going to be a bunch of constants times a bunch of functions of time. The constants are not going to be nailed down unless you have an initial condition. So I'm not talking about initial conditions now. I'm not talking about how far did you pull the spring back. I'm talking about the general case. What you get when you solve this guy with 0 here is going to be an infinite number of solutions because I'm going to have these constants running around. Okay, now I put my forcing function back in and I find what we call a particular solution due to the fact that this particular forcing function is pushing on my system or whatever it is. If it's an electric circuit, the forcing function might be a particular voltage source, with a particular frequency. Or that's sort of the details of what's pushing and what's forcing the system. And whenever I look at this, I'm going to get a particular solution. So mathematicians have studied these things long enough to figure out that when you have a linear equation driven by a source, the solution is always going to be split up like this. You're always going to be able to identify a part of the solution, if you cover this up, that's really only involved because of the particular driven source we have. And then the other part of the solution is always going to be totally, it's generic, but it's specific to how I've constructed my problem with my mass and my spring. If it's a circuit, it's going to depend on the values of the resistor, the values of the capacitor, how I've constructed the circuit. And these two things together describe the whole solution. It's very important that you understand that because later on, techniques are going to be used to exploit this. So I want to stop there right now. Hopefully you understand what I'm talking about, but what we're going to do here in just a few minutes is solve a few equations, actually from the beginning, and I'll be able to point to the solution and show you, look, this is the particular solution, P of t. This other part over here, this is the part of the homogeneous solution over here. So when you look at the generic stuff on the board, just like you do in a book, it doesn't make a whole lot of sense. But when we look at a few problems, I promise you, I'll be able to point and show you what these things are, and your eyes will open up a little bit, and it'll make a little bit more sense. So let's stop right with that, and let's do something else. What I want to do next is write a couple of differential equations on the board, maybe 3 or 4 of them, and we'll look and identify and ask ourselves, are these guys linear or nonlinear? And if they're linear, ordinary differential equations, given by the definition over there, are they homogeneous or are they non-homogeneous? So let's do that right now. So the first equation that we're going to look at, let's say we have d squared x, or I should say second derivative of t, the second derivative of x with respect to time, minus 5 times t times x equals t times dx dt minus 25. And the question that you need to ask yourself is this linear or nonlinear? And if it's linear, we're going to further ask ourselves, is it homogeneous or is it not? So you go back to your definition, and a lot of people stare at this and are like, I have no idea. Well, what you need to do is try to manipulate this and pull it into the form that I've written here on the board. That's really the only way to do it. So here I have a derivative, and in my definition, all my derivatives are on one side of the equal sign, so let me pull this derivative over here, right? So what I'm going to do when I do that is second derivative of x with respect to time minus t dx dt, just pulling this guy over with a minus sign. This guy stays the same, 5 times t times x, and I'm going to leave for now the negative 25 over on the right-hand side. Now look at this and tell yourself and ask yourself, is this linear or nonlinear? Well, let's look at our definition. We have nth derivative here, we have a second derivative here. The function of time in front of this guy, which is this guy right here, this a n of t, is just simply 1. Don't forget that a constant really is a function of time. It's just constant. So you get a 1 here. So this part so far makes sense. The next term, I have dx dt, and I have a function of time, a function of my independent variable right in front, which follows in line with how it would go. You know, second derivative, first derivative, and so on. Here's the first derivative. Here's my function of time. So it totally matches up there. The next term has a plain x by itself, which is what we have here. You're allowed to have a function of time in front of this x. Well, 5t is a function of time. So I have satisfied everything on the left-hand side. I have second derivative, first derivative, no derivative. Each one of them has a function of time in front, which totally matches everything here. On the right-hand side of the equal sign, do I have e of t, which is just another function of time, my forcing function. On the right-hand side of the equal sign, I have negative 25, which is a function of time. So that trips people up sometimes. You look at constants, and you're like, well, that's not a function of time. Well, don't forget that any constant really is a function of time. It just doesn't change. So this is my forcing function. If this circuit represented, let's say, you know, an electric circuit, if this differential equation represented an electric circuit, this E of t might be the voltage. Maybe I have a 25-volt battery, you know, hooked up backwards or something, so it's negative, hooked up to my circuit, a constant 25 volts, or maybe it's 25 amps going through the circuit as my sort of my forcing function. So that's what that is over there. So this guy's linear is sort of the bottom line because it matches up, so it's a linear. Right? It's linear. Now, next thing we want to ask is it homogeneous or is it non-homogeneous? Well, homogeneous means the forcing function E of t on the right-hand side is 0. Clearly, it's not 0, so it's non-homogeneous. Okay, so you just need to think about it a little bit and move these guys over and, you know, make some progress. Okay, the next thing is, what if I have dx dt, I'm going to wrap it in parentheses, let's square it, minus 2 times t squared. And that's equal to 0. Now let's ask ourselves this, is this linear or non-linear? And if it is linear, is it homogeneous or not? Well, let me look at this guy. Let's take a look at this. I have dx dt squared. Let me look over here. Does this match what I have on the board? It doesn't match. Because what I have over here, I have an nth order derivative with a function of time in the front. Here I have a first derivative that's squared. That is completely different than the second derivative here. So this is set up to be, you know, no derivative, first derivative, second derivative, third derivative, fourth derivative, however many you have up to nth derivatives. Nowhere in here does it tell you that you can wrap parentheses around a derivative and square it. That's totally changing it. I mean, I take my derivative and I square it. I might as well put a logarithm out here and wrap it up in a logarithm. That's nonlinear also. So this, just by the fact that I have a derivative squared like that, is nonlinear. So that was really easy to identify. Once you get to the fact that it's nonlinear, it makes no sense to talk about homogeneous or non-homogeneous. You might think, well, it's homogeneous, and I guess it kind of is, but the trump card is nonlinear equation. If it's nonlinear, none of these solution techniques that we're going to study in this part of studying differential equations are going to apply. That's why we're learning how to classify them, because they really all have to be linear to follow the techniques laid out here. You get to nonlinear equations like this, and they just become really, really difficult to do anything with. All right, next problem. let's say, what if we had second derivative of x with respect to time is equal to negative x times dx dt? And is this linear, is it nonlinear, et cetera, is what we're trying to figure out. Well, just like before, my advice is if you have derivatives on both sides, pull them over to one side of the equation. So let's do that here. So I have the second derivative here, dx, d squared x, dt squared. We'll move this guy over, plus x dx dt, and it's going to now equal 0 because I've moved it over. So we're going to go down the line and look at it. Here I have a second derivative that matches up with what I'm allowed to have here. The constant, or the function of time in front, is just a constant right here. So I'm set. Now the second term is the first derivative. Here I have a first derivative, and here you have a function of time here. You might think that this is linear, right? Because I have a nice, second derivative, first derivative, 0. So you might think it's a homogeneous linear equation. The problem is this x out here. Notice my definition. You can have a function of time, which is a function of your independent variable, which is time, the way I'm writing it on the board here. So because I have x here, this is not just a random old variable. This is the x of t that I'm trying to find, right? So nowhere in my definition is that allowed. I have nth derivative function of time, first derivative function of time, no derivative function of time. But nowhere is it allowed that I have a first derivative with the function I'm solving for out front. I can have functions of time out in front of the derivatives is really what I'm trying to say. So that kills it right there. There's nothing else to do. There's nothing else to look at. Yeah, it might have a 0, might look like it's homogeneous, but it absolutely makes no difference. It's nonlinear. Which basically means, for the purposes of this course, is that using the solution techniques that we're going to develop here over the next several sections aren't going to do anything. They're not going to be used. Okay. Finally, let's look at d fourth derivative of x with respect to time. Whoops, I need a 4 here. So this is a fourth derivative of x with respect to time plus 5 times t cubed times dx dt is equal to the square root of t squared minus 1. So I'm trying to figure out if this is linear or nonlinear. So I look at it and I really immediately realize I have derivatives. All my derivative terms are on one side of the equal sign. Let me go ahead and just make this a little bit clear here. All right, so far that's pretty good. Let's go down the line and see how it matches up. Here's a fourth derivative. Okay, so I have an nth derivative here. There's a constant out in front, so that doesn't have any problems here. This is a nice function of time, really. It's a constant, but it's a function of time. Now, there is no third derivative and there is no second derivative, but that's okay because if you think about it, if you kind of put them in here, if I kind of push this over to the right and I put a third derivative, then a second derivative, and then continued on, then in order to make it fit this definition, I could just pick my functions of time that sit out in front to be 0. Then this would be okay. So in other words, if I wrote this differential equation as fourth derivative plus 0 times a third derivative plus 0 times a second derivative, then they all disappear, but it still fits within my definition because the function of time for those two guys just happens to be 0. If that makes sense to you, great. Hopefully it does. But another way to think about it is, look, you can skip derivatives. It's okay. It's just that whatever you have there must conform to what the definition says. So let's look at first derivative. Here we have a first derivative, function of time. This is a pure function of time, so that checks out. On the right-hand side of the equal sign, all it says we have to have is a pure function of time, no x's. Here we have a pure function of time. So we have nice derivatives, we have nice functions of time in front of all my derivatives, have a nice pure function of time on the right-hand side, so this is linear. This is linear. Now, once we know it's linear, let's go figure out, is it homogeneous or is it not? The e of t that we have on the right-hand side is obviously not 0, so we say it's non-homogeneous. We say it's non-homogeneous. So it's really, really important that you know how to classify these things because, number one, you'll be asked on your exam, but also later on down the road, when you apply these solution techniques, you're going to have to know if it's homogeneous. You're going to have to know if it's non-homogeneous. And you're definitely going to have to know if it's linear or not. So take the time to learn how to do this so that you don't waste time later trying to do techniques to solve equations that are just not solvable by those methods. Well, that concludes this section. Really what I wanted to get out of this section was to introduce what a linear equation was, give you some practice identifying linear from nonlinear equations, homogeneous from non-homogeneous equations, and also introducing you to the fact that all of the solutions of these equations, these linear equations, can be busted out into a solution that deals with the homogeneous version when you set this equal to 0, and a term or terms that deal with being a particular solution to this equation with the forcing function that you have. So in general, you can always write a solution like this. Now what I want to do next is stop the section here, and in the very next section we're going to work a few problems to solve real equations, elementary, differential equations, and show you by real life examples that the solutions really do follow these forms. And we'll wrap it up and I'll kind of explain why that's important. So I'm Jason with MathTutorDVD.com. Hope you understand this, and if anything is at all not quite totally clear now, once we solve a few problems and I can show you how the solutions are busted out, I guarantee it'll make total sense. Learn anything at mathandscience.com.